Hi there. It's easy to share this hush with you. In the quiet of the room, your shoulders let go a little, and your breath moves like a small tide. You're safe here, nothing urgent, nothing bright, just a dim room, a calm voice, and the steady rhythm that carries you toward rest. Tonight, we'll hold a small ember of wonder in our hands and watch it glow. How do stars forge the elements? How does simple hydrogen become the iron in our blood, the calcium in our bones, the gold tucked in rings and memories? We won't rush. We'll drift slowly, like starlight across a window, from gentle fusion in newborn suns to the grand, unhurried fires that build carbon, oxygen, and beyond. We'll listen for the faint music of atoms finding each other, and follow it to the moment a star gives back everything it has made. If this gentle journey brings you ease, a soft like, and a quiet subscribe, help others find this calm, only if it feels right, only when you're ready. For now, let your shoulders loosen, let your thoughts float like dust in a sunbeam, and let the sky open just a little wider. Close your eyes, the stars are working, and we'll wander there together. Long before Earth had a name or seas learned ashore, the universe began with only the simplest notes, hydrogen and helium drifting in vast, quiet clouds, with just a whisper of lithium between them. On their own, they could not sketch a coastline, raise a cedar, or steady a heartbeat. Yet inside that plainness waited a patient promise, and the promise had a keeper. Stars would gather this softness, press it into fire, and slowly open what was hidden, teaching simple atoms to become breath, bone, and the small electric spark that carries a thought. Picture those early elements as flour and water on an empty counterplane, almost austere. Then imagine the ovens arriving, one by one, across a dark kitchen that stretches without end. Each star, a furnace, gentle at a distance, tremendous up close, reshaping matter under pressures and temperatures beyond anything our hands can hold. In those blazing cores, the bare ingredients of the newborn cosmos began to change, slowly, steadily, into the materials that would one day make ocean salt and mountain stone, the oxygen that lingers at the end of your inhale, the iron that rides quietly in your blood. Starlight became structure. Fusion turned lightness into weight and scattered that work across space like seeds flung from a patient hand. To feel this more closely, let the universe rewind until its first minutes, when space itself was new and hot and humming. Not an explosion ripping through emptiness, but expansion, the fabric of space, stretching from something unfathomably small into room enough for everything. For a brief while, conditions were too fierce for familiar matter to settle. Energy, particles, and radiation jostled and flashed in a restless crowd, too hurried to hold. As space widened, the temperature fell, and cooling acted like permission. Things could slow just enough to join. Within the first 3 minutes, the smallest building blocks, protons and neutrons, found one another and held fast. Here, the first elements took shape in their simplest forms. Hydrogen arrived first, one proton with an electron circling like a quiet companion. Helium followed, more solid in its stance, 2 protons and 2 neutrons bound together, the older, sturdier sibling. Lithium appeared as a trace, a shy afterthought at the edge of the recipe. This brief era, about 20 minutes long, is called Big Bang nucleosynthesis, a short chapter by cosmic standards, yet it stocked the shelves with the lightest essentials. About 3/4 of ordinary matter settled into hydrogen, about 1/4 into helium, with a thin scattering of lithium like a pinch of salt. Why stop there? Why not step directly to carbon for bones and diamonds, to oxygen for air, to iron for strength? The answer is a quiet rule about stability. In that dense, radiant beginning, anything heavier than lithium could not keep itself together. The crowd was too hot, too hurried. Complex nuclei fell apart as soon as they tried to gather. The universe paused at simplicity, and that pause turned out to be wise. 3 main ingredients: hydrogen, helium, and a dusting of lithium waited like flour, water, and salt. Out of patience and pressure, the rest would come. Hydrogen deserves a soft spotlight, the simplest atom, yet the most abundant even now. Billions of years later, unassuming, everywhere, utterly essential. Without hydrogen, there are no stars. Without stars, no long bloom of elements. Helium is quieter still, the ash left from hydrogen's slow burn, later called forward as fuel when conditions deepen. Lithium, gentle outlier, lives in traces and puzzles astronomers, with its shy behavior sometimes destroyed in stellar bellies, sometimes replenished later by curious roots. It slips in and out of ledgers like a character that prefers the margins, and its mystery remains part of the charm. So much of what matters to us came afterward. The oxygen cushioning your lungs, the calcium giving bone its whisper of stone, the silicon sleeping in sand, the iron lending blood its quiet red. The universe began like a bowl of clear broth, waiting for heat and time. There is wisdom in that restraint. Hydrogen and helium are wonderfully stable, and that stability let them endure long enough to gather. Under gravity's patient pull, those clouds thickened, drift by drift, until some parts grew dense and warm. From that slow gathering, stars kindled and kitchens lit across the dark. Gravity is the quiet chef that never tires. It tugs at every atom, every grain of gas, drawing scattered clouds into clumps, then knots, then spheres. The larger the cloud, the stronger the tug, the faster the fall inward. As the gas collapses, it heats friction and squeeze doing their work, pressure mounting at the center like a coiled spring. There is no match to strike, no spark to add. The oven preheats itself. When the core grows hot and dense enough, nuclear fusion begins, and the kitchen opens. Light appears as a byproduct of balance. Outward pressure from fusion pushing against the inward pull of gravity. For as long as that truce holds, a star lives. Fusion is the recipe itself. Light nuclei pressed together become something heavier. Protons naturally repel, like 2 north poles of a magnet refusing to meet. Yet, in a stellar core, the temperature and pressure are so intense that they can be forced close enough for the strong nuclear force to catch and hold them. When they fuse, a tiny bit of mass vanishes, turning into energy. Einstein's E equals mc2 whispered into action. That energy streams outward as light and warmth. Every twinkle above is fusion speaking across distance. Most stars spend their long first act fusing hydrogen into helium. In our sun, billions upon billions of hydrogen atoms merge every second. Each event releasing a breath of energy so small alone that it seems like nothing. Yet together it is daylight and weather and the slow engine of seasons. This is not hurried cooking. It has the patience of a stew left to thicken over low heat, flavors deepening without drama. The star's outer layers act like a lid, keeping the core steady so the simmer never breaks. As hydrogen thins in the center, gravity tightens its hand and the core contracts, heating further until helium can take the stage. Helium fusion knits carbon and oxygen, the bones and breath of life, out of that earlier ash. In stars more massive than our Sun, the sequence continues in layers, each shell using a different fuel. Hydrogen burns near the outer regions, helium beneath it, carbon deeper still, then neon, then oxygen, then silicon, down to a core that grows rich with iron. The structure resembles an onion, not by metaphor alone, but by function. Each ring, a distinct fire, each fire feeding the next, all of it held in balance by the eternal tug of gravity. In the most massive stars, the kitchen becomes a roar. Core temperatures climb to hundreds of millions of degrees, fierce enough to fuse elements all the way to iron. There, the ladder ends, because iron does not pay back energy when fused. It keeps what it is given. Beyond that point, fusion can no longer help hold gravity at bay. The star's life is measured by how long those outward pushes can match the inward pull. While the balance lasts, the star endures. When it fails, something dramatic follows. But for now, it's enough to feel the poise fusion pressing outward, gravity drawing inward, a long, stable breath that can last for billions of years. Our Sun is modest. It will not climb far into that onion, will not drive its core to carbon fusion, will not rage as a blue-white giant. It will spend its time as a faithful oven, turning hydrogen into helium with dependable grace, bathing this small world in warmth. From that steady gift come leaf and cell, tide and weather, the soft stir of wind through grass, the rhythm beneath your ribs. Patience is one of the loveliest qualities of stars. Some live fast, running through their fuel in only a few million years, like a cook who always turns the burner a little too high. Others, the red dwarfs, burn so slowly they can last for trillions of years longer than the universe has existed so far. They are the masters of the low flame, stretching their ingredients across distances of time we can't truly hold in mind. Between those extremes lies a garden of lives and endings, each star keeping its own pace. It is easy to think of stars as fixed points. From our distance, their shimmer looks calm, like pinpricks in fabric. But inside, a star is a busy, self-regulating city of heat and pressure and light. The scales are bewildering. A spoonful of the sun's core would weigh more than a mountain and outshine any furnace we can build. Yet seen from here, there is only a gentle glow, arriving after long travel, softened by air and distance, generous to eyes that want rest. Calling stars kitchens is not just a sweet image, it's practical truth. Without stellar ovens, the universe would remain a thin broth of hydrogen and helium. With them, it becomes a table set with variety. Carbon for life's scaffolding, oxygen for breath and water, nitrogen for proteins and air's quiet cushion, silicon for rock and glass, iron for red blood and bridges, and on through a catalogue of presents. Galaxies eat from this table. Worlds do too. So do we. Consider the humility of the recipe. Start with almost nothing. Hydrogen in abundance. Helium as its faithful shadow. Lithium barely there. Add gravity and time. Allow collapse and heat to invite fusion. Let light seep out as a sign that the balance holds. When the first fuel wanes, allow another to step forward. In the giants, stack shells upon shells until iron marks the limit. Then return those elements to the dark between stars, sometimes gently through stellar winds, sometimes in a single drastic breath. In the long after, new clouds inherit those ingredients, and the cycle repeats. Stars from ashes, ashes from stars. There is tenderness in the idea that the oxygen in your lungs was once pressed toward being in a place with no wind, no sky, only the logic of a core. That the calcium in bone learned its shape in a furnace you will never see. That the iron passing through your blood began as sunlight's raw material. To know this does not demand any grand gesture. It invites a quieter feeling, kinship with the soft, steady processes that keep the night lit. Hydrogen, helium, lithium, 3 humble notes, about 3/4, about 1/4, a trace, a universe cooling enough to let hands clasp, then waiting long enough for fire to teach form. Gravity making invitations that could not be refused. Fusion answering with warmth. For billions of years, that has been the rhythm. Gather, heat, hold, transform, release. The sequence repeats across distances too large to map and times too long to count. And yet it reaches into a single room, into the slow rise and fall of your breath. If you step outside on a clear night, you might feel that the stars are decorations, distant and small. It helps to remember what they are doing. Each light is a sign of work underway, an oven keeping balance under its own weight, a recipe carried out at scales where patience is the only option. The glow you see is energy traveling across emptiness, telling quietly of atoms changing partners, little by little, over spans so wide that history itself feels like a passing dream. Those changes build the familiar rock and rain, salt and sap, shell and seed, skin and thought. There is nothing hurried here. The cosmos learned not to rush. It began with almost nothing and leaned into time until variety could flower. You belong to that patience. You carry a ledger written in elements that learn their letters in flame. The air you draw in is older than any story we tell, and the star-made metals in your blood were cast in places where no voice can travel. Even the smallest gesture, your chest lifting, your shoulders easing, happens because of choices made in stellar cores long ago. Think of a baker who returns to the same bread day after day, trusting flour and heat and the quiet chemistry of rise. The universe is like that, faithful to a short list of rules and endless in the ways it applies them. From hydrogen's first gatherings to helium's steady ash, from carbon's branching possibilities to oxygen's easy bonds, from silicon's hard spine to iron's final calm. The work continued until there was enough on the table for oceans to roll and forests to breathe and eyes to open. The next time starlight finds your window, let it be more than a pretty scatter. Let it be a background hum you can lean against gravity and fusion keeping their truce. Heat wandering outward, matter learning new shapes. You're looking at kitchens that have been open for billions of years, perfecting a menu that eventually placed you here. The recipe is both fierce and gentle. The scales are violent. The results are graceful. Rest with that for a moment. The soft shine overhead is atoms becoming something new, and a little of that work is happening in you now, quiet as a resting pulse, warm as a hand in the dark. From that hum, a simple truth steps forward. Every star you can name is both a fire and a quiet vow. Given time and patience, even the simplest things become extraordinary. Fusion is that vow kept a steady hearth, more than a blaze, taking the barest atoms and pressing them close until they agree to be something new. No alembics, no whispered potions, just nature's calm craft, building complexity from simplicity, slowly and surely across the ages. Begin with hydrogen, the humblest note in the score. One proton at its center, one electron moving like a faithful moon, modest everywhere, and at the root of almost everything you have ever known. When 4 of these light hearts are coaxed together in a stellar core, helium appears, and with it, a spill of energy bright enough to light worlds. It feels like a secret hydrogen has carried since the first dawn, an ability to turn mass into radiance. The difficulty is the first touch. Protons carry positive charge, and positives push each other away, like 2 north poles of magnets refusing to meet. In ordinary rooms, fusion never starts. But stars are not ordinary rooms. Cores climb to millions of degrees, pressures rise beyond any furnace we can build, and particles are hurled so fast that they collide before they can fully repel. Cross that tiny gap, and a different force wakes the strong nuclear force, shy at a distance, irresistible up close. It is the glue of nuclei, doing almost nothing until 2 particles come so near that it can clasp them with a grip stronger than anything else we know. In that instant, 2 become 1, and the ledger of mass shortens by the smallest amount. Nothing is lost. The missing fraction becomes energy, carried outward as light and warmth by E equals mc. 2. A line of ink turned into sunlight. Repeat this in countless reactions. Every heartbeat of a star, and you get the glow that travels for millions, sometimes billions of years, to arrive as a soft shimmer at your window. Hydrogen fusion is the steady thrum of stellar life. Yet even the most generous pantry runs lower with use. When the center of a star begins to run short on hydrogen, gravity tightens its hand. The core contracts, heats further, and another door opens. Helium can fuse. 2 protons repel more strongly than 1, so the threshold is higher, the oven hotter, the patience deeper. When the conditions are right, 3 helium nuclei, 3 alpha particles, meet in a delicate choreography called the triple alpha process, joining to become carbon. Out of helium's ash, a backbone for life appears. From there, a gentle ladder rises. Add another helium nucleus, and carbon becomes oxygen. Continue with heat and time, and you can knit neon, magnesium, silicon, sulfur. In large stars, this work arranges itself in shells, each layer burning a different fuel, stacked like an onion's rings, each ring a separate fire, each fire feeding the next. There is, however, a soft limit written into the math of binding. Fusion shines because the nucleus you make is more tightly held together than the ones you started with. The difference is paid out as energy. Climb high enough, and the payoff fades. At iron, the account breaks even. Try to fuse iron into something heavier, and you must spend energy instead of earning it. Iron is a cosmic full stop, a point of perfect stability. Beyond it, the usual stellar kitchen can't push further. When a massive star's center fills with iron, gravity finds no outward pressure left to balance it. The core collapses in a breath. What follows can be a supernova, a brief, furious unmaking and remaking that throws the star's outer layers into space and kindles new elements in a storm of particles and heat. This is where the heavier children, nickel, copper, zinc, and onward begin to appear in earnest, forged not by steady simmer, but by catastrophe. Our sun will keep to calmer paths. It is not heavy enough to reach those extremes. After a long life fusing hydrogen to helium, it will swell, shed its outer layers in a gentle glow, and retire as a white dwarf made mostly of carbon and oxygen, an ember that will cool for eons. The grand staircase to iron belongs to larger stars, and the steps grow hotter and narrower as they climb. Hydrogen to helium, helium to carbon and oxygen, then to neon, magnesium, silicon, finally iron, where the ledger stops. Each stage is fiercer than the last, and each is part of the same balancing act. Outward push from fusion, inward pull from gravity, kept in poise until the final arithmetic fails. The alchemy of fusion is the universe's oldest craft. It turns a nearly empty stage, a thin mist of hydrogen and helium, into galaxies of light, and then into the elements that make rock and rain, leaf and lung. There is nothing rushed in it. Think not of explosions, but of a constant fire that holds its temperature for billions of years. Stars are patient cooks. They stir slowly. They wait for conditions to ripen. They keep the flame just where it must be, and let time do the soul of the work. In the carbon woven into your cells, and the oxygen riding your next breath, that fire left its fingerprints. You are, in the plainest sense, a keepsake from the kitchens of stars. Look, then, at the periodic table with softer eyes. It is not merely a classroom grid, tidy and square. It is a map of origin stories. Most squares trace back to either the calm interiors of stars, the sudden violence of supernovae, or the rarer collisions of neutron stars. What seems like a chart is more like an atlas of furnaces. Begin at the far left. Hydrogen, the simplest and most abundant, born minutes after the Big Bang, the common seed of nearly everything. Beside it, helium, also from those first instants, airy in balloons, here on Earth, but in space, a byword for stability and grace. Together, hydrogen and helium make up about 99% of normal matter. Two words could summarize the cosmos, and they would do. Move inward, and the table begins to sound like home. Carbon, nitrogen, oxygen, names that feel like familiar neighbors. Stars earned them the hard way. Helium nuclei fused to carbon. Carbon folded into oxygen in old warming cores. Nitrogen gathered in the complex lives of large stars, and later joined the chemistry of life. Their squares sit together not by accident. Their positions echo their shared paths of birth. Families gather in columns for chemical reasons, and those families also whisper of stellar ancestry. Further along sits the machinery of worlds. Silicon, magnesium, iron. Silicon and oxygen bind to make rock and sand. Magnesium lends strength to minerals. Iron settles to the centers of planets and finds its way into bridges and blood. Iron is also the quiet gate at the end of ordinary fusion, the point where a star's kitchen goes dark unless some crisis arrives. Past iron, new rules take over. To build gold, platinum, uranium, and their heavy kin, you need crowds of neutrons and a flood of energy that steady burning can't supply. A supernova provides one way. In the brief roar, after a massive star's core gives way, temperatures and pressures leap beyond everyday stellar life. Neutrons stream through the ejected layers, and nuclei capture them in a rush. Some of those captures stick long enough for new elements to form. In that hail of particles and light, iodine finds its path. Gold takes shape, and uranium climbs to its heavy throne. Rarer still is another kind of forge, the collision of two neutron stars, the dense remnants left after some supernovae. Imagine matter squeezed so tightly that a teaspoon would outweigh mountains. When two such remnants spiral together and merge, the universe briefly opens a gate to conditions unlike any others. Neutrons flood into waiting nuclei and assemble some of the heaviest, rarest elements we know, platinum among them. Entire galaxies may wait millions of years between such events. Yet the atoms born in those moments drift outward, settle into dust and clouds, and eventually join new planets and people. A ring on a finger can carry the memory of two dead stars touching after a dance longer than civilization. The table, then, is not a quilt of colors but a family tree. Hydrogen and helium from the first minutes. Carbon, oxygen, silicon from the steady work of aging stars. Gold and platinum from brief catastrophes. Each square a small address label, forged here by this process, under that pressure and heat. Dmitri Mendeleev sketched his chart in the 19th century by watching how elements behave with one another, how eager they are to give or take electrons, how they bond, how they react. He could not have known that his groupings would mirror stories written in stars. Place oxygen in its column with sulfur and selenium, and you gather not just shared chemistry, but a shared history in stellar fusion. List the noble gases helium, neon, argon, and you name a lineage of stability. Atoms so complete in their electron shells that they rarely bother to react. A calm that reflects the stable paths of their formation. Read the grid like a book. Rows mark changes in electron shells, which is a way of saying they mark stages of possibility. Columns show kinships, which is a way of saying they show families with similar habits and, often, similar cosmic roots. The elegance is humbling. The universe is not random in its abundance. The most common elements are exactly the ones most useful for structure and life. Hydrogen fuels stars and helps make water. Carbon is a champion of variety, forming chains and rings that hold biology together. Oxygen partners with hydrogen for oceans and with carbon for breath. Silicon and iron build planets and let them keep their shape. Even the rarest elements, present only in whispers. Matter, phosphorus stitching through DNA, iodine guiding hormones, copper coloring blood chemistry in some creatures, and carrying current in the tools we make. This is not destiny in any mystical sense. It is physics, the shapes of nuclei, the costs and gains of binding, the thresholds where fusion pays and where it does not, the ways electrons settle. The table reflects what is possible. The universe explored those possibilities thoroughly, filling in squares not because it aimed at us, but because the rules allowed those squares to exist, and time was long. Nothing is wasted. Trace elements tilt the behavior of rocks, help enzymes fold, tint the shells of beetles, steady the beats of hearts, steer the signals in nerves. Even the shy ones have jobs. Hold a stone, and you are keeping a record of stellar fusion in your palm. Sip water, and you taste a union of ancient hydrogen with oxygen born in the hearts of stars. Glance at a golden ring, and you glimpse the echo of a neutron star wedding that might have happened billions of years ago, far from here. The periodic table is the universe's autobiography told in symbols and numbers. To know it a little is to sense how stars lived and died and shared their work. To feel it deeply is to notice the kinship between a person breathing in a quiet room and a furnace burning in a distant night. What comforts most is the steadiness of it all. Fusion may pause at iron inside ordinary stars, but its legacy does not. Elements scatter, gather again, and begin fresh stories in new places. Clouds inherit what earlier stars made, collapse and light up. Planets form from the leftovers. Life tries ways of being. Minds learn to name. Across it all, the same few rules do the lifting. Gravity folds. Pressure rises. Fusion answers. Light travels. Matter rearranges, and the table fills. You carry that history quietly, carbon in bone, oxygen in breath, iron in blood, iodine keeping small balances in your throat. The stars wrote the recipe and mailed it across time. Your body reads it without a sound. So when you look up at a sky freckled with light, think of kitchens still at work, hydrogen learning to be helium, helium joining to become carbon and oxygen, layers growing like rings in a tree, ions setting a final limit that forces a new kind of creation, rare collisions, sprinkling the heavy metals we cherish. The table on a classroom wall isn't just a chart to memorize. It's a map of journeys, some calm, some sudden, all connected. Underneath is a simple, warm truth. Given time, the universe turns simplicity into depth. Stars keep the flame. Fusion keeps the promise. And a little of that promise is living in you tonight. Steady as a resting pulse, patient as starlight crossing the dark. Follow that map into a single square and watch it open like a door. Within those neat boxes lies a quiet truth. Everything around you and everything within you belongs to the same cosmic recipe. Begin with carbon, which looks too modest for the role it plays. It doesn't gleam like gold, announce itself like oxygen, or abound like hydrogen. Yet, it serves as life's chief architect. Without it, no spiraling DNA, no proteins folding into delicate shapes, no sugars to feed our cells, no forests leaning into the wind. Carbon is the backbone of biology, a central pillar holding so much living form, and the story of how it came to be is as extraordinary as the part it plays. Hydrogen fusion keeps stars shining, but helium fusion opens the door to carbon. When a star's core runs low on hydrogen, gravity presses inward, turning the furnace to a higher setting. At roughly 100 million degrees, a special choreography begins. The triple alpha reaction. The name sounds technical. The idea is elegantly simple. Helium nuclei alpha particles are wonderfully stable, and yet under immense heat and pressure, they can be persuaded to join. First, two helium nuclei collide to form beryllium-8, a fragile arrangement that normally falls apart in an instant. If, in that brief heartbeat, a third helium nucleus arrives, the three merge to form carbon-1,2. It is like catching lightning in a bottle, a fleeting chance rescued into permanence. The carbon nucleus carries an energy level that lines up just so with this dance, making the improbable suddenly productive. The balance here is delicate. Three helium particles meeting at just the right moment is rare. For it to happen often enough to make the carbon we see, the energies inside the carbon nucleus must align with uncanny precision. Some people call this fine-tuning. Others see it as the natural outcome of physical laws we are still learning to understand. Either way, the result is the same. The cosmos found a workable path to carbon, and with it, the possibility of life. Stars not only forge carbon, they scatter it. Medium-sized stars end with gentleness, shedding outer layers as drifting shells of gas and dust that carry carbon into space. Large stars end with drama. In supernovae, shockwaves blast carbon and many other elements across their galaxies. Over billions of years, these atoms wander, settle into clouds, and become new stars, new planets, and eventually, living hands and lungs and eyes. What makes carbon special is not just that it exists, but what it can do. Each carbon atom can form 4 bonds at once, which is like having 4 calm hands ready to build. It links into long chains, closes itself into rings, or branches into intricate frameworks. No other element offers the same blend of stability and flexibility. The box of carbon blocks can be assembled into almost any shape you can imagine. That's why organic chemistry, carbon chemistry, is the foundation of life. Carbon forms the spine of DNA, the spiral staircase that carries genetic memory. It shapes proteins, the tiny machines that do nearly every job inside a cell. It builds carbohydrates and fats, storing energy and shaping membranes. Even the simple act of breathing relies on carbon dioxide, where carbon holds oxygen's hand for a time. Outside biology, carbon keeps revealing new faces. Arrange its atoms in flat sheets, and you have graphite, soft enough to leave a mark with a touch. Lock them into a tight lattice, and you have diamond, among the hardest solids we know. Curve them into hollow spheres, fullerenes, or roll them into nanotubes, and they gain strange, useful traits. Carbon is that versatile artisan who can knit lace in the morning and forge armor by night. On Earth, carbon moves in a long, careful rhythm. It cycles between air, ocean, soil, and living things. Plants take in carbon dioxide, turn it into sugars, and release oxygen. Animals eat the plants, breathe out carbon dioxide, and return it to the sky. Some carbon slips into stone or dissolves in the sea. This circulation keeps carbon available in forms life can use, while also helping steady the climate. If the cycle tips too far, climates shift, ecosystems lean, and the conditions for life grow fragile. In that way, carbon is both a gift and a responsibility, reminding us of our link to the stars above and the ground beneath our feet. There's a tender kind of poetry at the personal scale. The carbon in your body, in every breath, every heartbeat, every passing thought, was born in stars that died long ago. The atoms that feed your brain were once pressed into being in a stellar core, then flung across the galaxy, then folded into the dust that circled a young Sunday. You aren't vaguely made of stardust. You are made of carbon atoms forged by fire, carried through cold space, and patiently assembled into life. Without carbon, the universe would be recognizable but lonely. Stars would still shine, galaxies would still whirl, but life, at least as we know it, would likely fall silent. People have imagined silicon-based life, and perhaps somewhere it exists, but nothing yet rivals carbon's easy generosity. Carbon is the quiet architect not because it demands attention, but because it patiently builds what matters. One kind of atom, no larger than a whisper, can give rise to forms almost without end, from the clean blaze of diamond to the soft staircase of DNA. Carbon is everywhere, shaping what we see and what we can only sense. The next time you breathe out, notice the carbon dioxide drifting from your lungs. Those atoms began in a star billions of years before Earth took shape. They may someday settle into a leaf, a shell, a mountain, or another living being. Carbon's story is not only the story of life, it's the story of continuity, an unbroken thread connecting stars, planets, and people. It is the quiet architect of existence, always working, never boasting, building the structures of the cosmos one bond at a time. Oxygen feels as familiar as breath, and yet its origin is as strange and spectacular as anything in the sky. It is the invisible companion that keeps cells alive with each inhale. It binds with hydrogen to form water, shaping oceans, rivers, and rain. It hides in rocks and minerals, making up much of the crust beneath your feet. If carbon is the architect, oxygen is the breath that keeps the whole structure humming. And like so much else, it began in stellar fire. Oxygen's birth picks up where carbon leaves off in the hot heart of a star that has already mastered helium fusion. The triple alpha process builds carbon, and then helium nuclei can collide with that carbon scaffold to make oxygen. The physics is simple in idea, immense in scale. You need temperatures in the hundreds of millions of degrees so helium can slam into carbon with enough force to merge. Once formed, oxygen is stable and tends to accumulate in large amounts. In fact, oxygen is the third most abundant element in the universe after hydrogen and helium. The atoms that now rush in and out of your lungs were once trapped in stellar cores, forged in pressure and heat. When those stars reached their ends, they released oxygen into space, some gently, as smaller stars shed their outer layers, and some violently, in the shock waves of supernovae. Over time, those atoms became part of new solar systems, new planets, and eventually, living beings. On Earth, oxygen's presence has shaped almost everything. It makes up roughly 1/5 of our atmosphere, yet it wasn't always there to breathe. For the first couple of billion years, the air held little to no free oxygen. The world was rich in carbon dioxide, methane, and nitrogen. Oxygen was locked in minerals or dissolved in seas. Life began without it, following chemical paths that needed no oxygen at all. Then something extraordinary happened. Microorganisms learned to use sunlight to split water and release oxygen photosynthesis. At first, that oxygen rusted the oceans, binding with iron and settling into vast bands of ore. Only after long ages did oxygen begin to build up in the air, in what we now call the Great Oxidation Event. It was a turning point for the planet and for life. Oxygen allowed bodies to release energy more efficiently, clearing the way for complex, multicellular creatures. Every animal that breathes today, including us, owes a quiet debt to that slow, world-changing rise. The link between stellar birth and planetary breath is deep. Oxygen atoms created in stars were scattered through the galaxy, gathered into the cloud that became our solar system, and folded into Earth. Here they became part of water, carbon dioxide, and countless minerals. Then life set them free again, lifting them back into the air. What stars began, life continued. The breath in your chest is the end of a chain that started billions of years ago inside a star. Oxygen's versatility makes it indispensable to bodies and to worlds. In water, it partners with hydrogen to make chemistry mobile. In rocks, it binds with silicon to form silicates, the most common minerals in Earth's crust. In your blood, it holds to iron inside hemoglobin and rides the current to your cells. Oxygen's gift is a bond that can be steady and yet ready, stable enough to build with, reactive enough to move energy where it's needed. Even breathing itself is an exchange, written in oxygen's script. Inhale, oxygen crosses into the blood. It joins hemoglobin, travels, and at the cell, helps break down sugars to release energy. The waste carbon dioxide rides back the other way and is breathed out. This quiet rhythm, draw in, let go, links a stellar past to a living present. On a planetary scale, oxygen gives and takes. It feeds fire, weathers rock, rusts metal, and patiently reshapes landscapes. Without oxygen, there would be no flames, no corrosion, no wide blue overhead, the tint of the sky, the sparkle of water, the colors of sunrise and sunset, each carries oxygen's signature. Free oxygen also seems rare elsewhere. Because it reacts so eagerly, it doesn't linger unless it is constantly replenished, usually by life. That's why astronomers who search distant worlds listen for oxygen in alien skies. If we ever find an exoplanet with abundant oxygen, it may be one of the strongest hints that life is working there, sending up a signal in chemistry's own light. It's easy to take oxygen for granted. Each breath feels effortless, a background hum. But every molecule you inhale is a survivor of a long journey forged in a stellar core, scattered across a galaxy, locked in stone, freed by microbes, and finally invited into your lungs. Oxygen is not ordinary. It is a traveler that moved through epochs and processes beyond imagination before joining your story. And where oxygen hints at journeys that continue, iron reminds us where journeys pause. Iron is the universe's punctuation mark, the small, steady dot that signals an ending. For a star, it is the place the kitchen goes quiet, the point where the careful recipe of fusion runs out of steps. In that modest metal is a graceful truth. Stars endure by balance outward light against inward weight, and iron is where that balance finally slips, teaching the sky how endings become beginnings again. Inside a star, fusion is a slow and faithful cook. Hydrogen becomes helium. Helium, when the core tightens and grows hotter, becomes carbon and oxygen. In larger furnaces, layers ignite and turn neon, magnesium, silicon, each step paying out a little energy, each payment pushing outward against gravity's inward pull. The star stands because two forces meet in truce, fusion holding up, gravity holding in. Take away the outward pressure, and gravity would crush the whole sphere to cinders. Take away gravity, and fusion would never light. The miracle is their long stalemate, a peace kept for millions or billions of years. But this peace lasts only while fusion pays. And fusion pays only while the nucleus you make is more stable, tighter bound than the nuclei you began with. Iron sits where the prophets end. Its nucleus is so snugly held together that trying to fuse it into something heavier demands energy instead of releasing it. The ledger turns red. A star that builds an iron core finds that its one defense, fresh fusion in the center, has become a wall. Gravity does not negotiate. It keeps pressing, quiet and relentless, until the core yields. What follows is the swiftest turn in a story that took ages to set the stage. Picture a core roughly the size of Earth, crowded with iron and neighboring elements, suddenly losing its inner support. In less than a second, it gives way. Atoms are crushed past their ordinary selves. Protons and electrons are forced together into neutrons. The heart of the star collapses into a ball so dense a teaspoon of it would outweigh mountains. Around that newborn neutron core, the falling layers slam inward, hit, and rebound. A shockwave races outward, tearing the star apart. To eyes far away, a point of light flares and briefly outshines an entire galaxy. To the universe, it is a storm, heat, particles, neutrinos ripping and remaking matter in a fever that lasts only moments. Iron, which ended one kind of creation, becomes the doorway to another. In the crush and heat of a supernova, elements heavier than iron can finally be assembled. Neutrons flood into nuclei. Some stick, some do not, but enough remain for new atoms to be born: gold and silver, iodine and barium, uranium, and more. The full stop at the end of a star's sentence becomes the place a new paragraph begins. Iron itself is everywhere. It anchors the Earth's deep core, helping drive a magnetic field that shields life from harsh solar winds and cosmic particles. It rides in your blood as hemoglobin, clasping oxygen and ferrying it from lung to tissue. Each breath depends on iron's elegant grip. Each turn of a compass needle depends on the planet's iron heart. The same element that signals stellar death is the one that lets bodies breathe and worlds keep a gentle, protective veil. Trace the iron in your body and you get a chain of events that began before the sun formed. A massive star lived its long life, burned through hydrogen and helium, stacked shells of heavier fuel, and built an iron core. When fusion could not pay the bill, gravity collected. The star collapsed and exploded, scattering iron into the surrounding space. Those ashes mingled with a cloud of gas and dust that would become our solar system. From that old star's last breath, Earth inherited iron. From Earth's iron, you inherited the atoms carrying oxygen through you now. A simple nail on a workbench is more than a tool. It's a souvenir from a star's ending. A stone rich in iron ore is a storybook from a supernova. Your own pulse is iron at work, tying your minutes to ancient fire. In a sentence, a full stop is an ending. In the sky, iron's full stop is also a pause before a new sentence begins. The star that made it is finished. The collapse, the flash, the dispersal, those are closures. Yet for the wider universe, each closure is an opening. The death of one star seeds the chemistry for new worlds. It enriches clouds, sparks new collapses, and sets stage after stage for rivers, rocks, roots, and breath. Iron is both final and fertile, stern and generous. Stars are patient cooks, but patience meets a limit. When iron arrives, the kitchen shudders. Gravity takes the pen, writes a furious chapter, and hands the ash to space. Without iron's stubborn stability, there would be no such endings. And without those endings, the heaviest elements would be scarce to the point of absence. Earth, in anything like its current form, might never have appeared. Iron is not just another square on a chart. It is the hinge on which stellar lives swing. It's the quiet signal that says, enough then. Just as quietly, it helps ensure the story goes on elsewhere. Few scenes are as dramatic as the moment a supernova blooms. A star that was ordinary to our eyes seems to ignite overnight, shining brighter than billions of neighbors. To us, it's a sudden spark in the dark. To the star, it's the end of long labor and the start of a cascade that will echo for ages. Step back into that layered kitchen to understand why. Over lifetimes, a massive star stacks fires within fires. Hydrogen shells feed helium. Helium shells feed carbon and oxygen. Deeper still, neon and magnesium. Deeper still, silicon. Each ring burning a different fuel. Each ring a distinct season. At the very center sits iron, the hard stop. Fusion can't help there, so the balance fails. Gravity tightens its grip on the core until the floor falls out. Picture something the size of a planet crushed to a sphere a few kilometers wide, and all of it happening in less than a second. The halt is so abrupt that a shockwave bursts outward. The star's own layers, still raining down, slam into that wave and are hurled into space. For a short while, the explosion can outshine entire galaxies. In the chaos of those seconds, the universe accomplishes work it cannot do in calm. Nuclei are torn apart and reforged. Neutrons pour through matter, and heavy elements grow rapidly in the storm. Gold finds its shape. Silver, too. Iodine, which later threads through the work of your throat, takes form. Uranium climbs to its heavy place. These atoms cannot be made in the gentle simmer of ordinary stellar life. They require the fierce, brief forge of catastrophe. Supernovae are rare in human time. In a galaxy like the Milky Way, they may ignite only once or twice in a century, yet their after effects last and last. Their shockwaves sweep up gas and dust, squeezing clouds until gravity can take over and new stars can be born. They lace the galaxy with heavy elements so that future planets can be rocky, future oceans salty, future bodies complex. Each explosion is both an ending and a planting, a clearing of old growth and a scattering of seeds. Humans have been quiet witnesses to this cycle. Long before telescopes, sky watchers noted guest stars that appeared where the heavens had been steady, glow for weeks or months, then fade. One in the year 1054 left behind the Crab Nebula, a tangle of glowing threads painted across the dark. Today we watch supernovae with instruments that can read their light like a letter. We measure which elements bloom and which fade. We track the shapes of their debris. We follow how the shock front moves through space. The remains are beautiful clouds expanding over light years, their colors hinting at their contents. Reds from hydrogen, greens from oxygen, blues from hotter, rarer light. They aren't just pretty. They are raw materials for worlds to come. These blasts also play a quieter role in keeping galaxies lively. Their energy stirs the interstellar medium, mixing it, preventing the kind of stillness that would starve new stars of the right conditions. Without these stirrings, a galaxy might become chemically dull. With them, a galaxy remains restless and creative, its future generations richer in the ingredients needed for complexity. What ties the spectacle to us is simple. The matter in our bodies carries the marks of these endings. Iron in blood, calcium in bone, copper in nerves, each rode a shockwave once. To look at your hand is to see atoms that were once parts of stars, thrown outward at absurd speeds, cooled, gathered, and given new jobs. You are, in a gentle and literal sense, the aftermath of explosions. For all their violence, supernovae are not unruly. They follow the rules with precision. Core collapses obey gravity. Neutrons form because quantum limits and energy balances demand it. Shock waves carry energy outward, and light reports what happened. There is variety. Some supernovae are the deaths of massive solitary stars. Others happen when a white dwarf in a close pair steals enough matter from its companion to ignite in a thermonuclear flash. But the outcome is always similar: a sudden flood of light and a scattering of elements that will one day build new things. Stand near one if you could, and you'd see light so bright it would erase shadows. Hear nothing because space is silent, and feel radiation that could scour worlds clean. From a safer distance, there is only wonder. Supernovae remind us the universe is not frozen. It changes by cycle. Gather, burn, balance, fail, explode, seed, begin again. Think of the chain. A cloud of hydrogen and helium cools and thickens. A star forms and carries its slow labor for ages. It climbs the ladder of fusion, reaches iron, and the balance ends. The collapse writes a flash. The flash writes elements. The elements ride outward and find their way into new clouds. Those clouds become planets. On one planet, oceans form, minerals settle, life finds a foothold, breath begins. Your breath is part of that chain. The distance between a star's last second and the quiet rise of your chest is long, but the link is unbroken. When you hear the word supernova, let the mind set aside only the idea of a blast. Think of a recipe with patience built in. Ingredients measured over eons, heat and pressure patiently applied, and then, at the end, a flourish. It is the universe seasoning itself, giving flavor to a broth that would otherwise stay thin, hydrogen and helium, and not much else. With supernovae, the cosmos becomes stocked with metals and minerals and interesting paths for chemistry to follow. With them, rocks can form, water can flow, tools can be made, songs can be sung. Any bright star you meet tonight may hold one of these fates. Some will live modestly and fade, leaving quiet remnants. The most massive will end in fire, casting their gathered riches into space. None of it is wasted. Their ash becomes soil for new worlds. Their elements will find their way into lungs and oceans and mines. Even as stars close their kitchens, they lay out the ingredients for future meals. Iron sits at the hinge stern, necessary and strangely kind. It ends a star's labor and makes the finale possible. It fills a compass and a bloodstream, waits in mountain and nail. It is the dot at the end of a sentence and the breath before the next. The sky's grammar is generous that way, an ending that behaves like a promise, a quiet mark that says there will be more, because when a star stops at iron, it doesn't hoard what it made. It tips the board, and in that tipping, the rarest pages of the recipe open. Out of that full stop, a different light steps forward. Gold and platinum carry a glow that feels older than memory. For a very long time, we've lifted them from rivers and rock, warmed them in our hands, shaped them into rings and crowns, tucked them away as tokens of safety. Their shine is undeniable, but the true story runs deeper than human years. Hold a piece of gold, and you're holding a relic from the universe's most extreme moments. Brief, blazing collisions and explosive endings where ordinary words thin out and the elements finish their longest journey into brilliance. The usual kitchens of the cosmos, those patient stellar furnaces that turn hydrogen into helium and then into heavier elements, can climb only so far. Fusion is generous until it reaches iron, and there the ledger closes. To step beyond iron, nature needs a different workshop altogether. A place where neutrons arrive in torrential crowds and slam into nuclei faster than those nuclei can fall apart. This is the rapid neutron capture path, the R process, and it doesn't run every day. It needs energy and density that ordinary stars can't provide. And for a long time we guessed where such conditions might appear, but the arithmetic didn't quite settle. Supernovae looked like the answer. A collapsing, exploding star clearly unleashes a flood of energy, and some heavy elements do rise in those storms. But the totals came up short. The universe held more R-process treasures, gold and platinum, thorium and uranium, than traditional supernova models could comfortably explain. The puzzle lingered like a soft pressure at the edge of understanding, until attention shifted to something rarer and stranger, the collision of neutron stars. Neutron stars are what remain when massive stars die and leave their cores behind, crushed into spheres only a few dozen kilometers wide. They are so dense that a teaspoon of their matter would outweigh mountains. Inside, neutrons are packed shoulder to shoulder in a way matter never attempts elsewhere. When two of these remnants find each other, they circle for a long time, losing energy in faint ripples that move through space itself, gravitational waves. Bit by bit, they draw closer until the orbit tightens and the final embrace can't be delayed. The meeting of two neutron stars lights a transient called a kilonova. It shines fiercely, but its light tells a special tale. Matter flung outward at astonishing speeds, bathed in a flood of neutrons. In fractions of a second, nuclei swallow neutrons again and again, then reshuffle through radioactive steps into stable, heavy elements. Gold and platinum pour into existence, along with a suite of rare companions, made in quantities that dwarf anything ever pulled from Earth. One collision can make riches that would weigh more than the world we stand on. In 2017, the universe gave us a clean, unforgettable demonstration. Gravitational wave detectors felt the ripples from two neutron stars merging, and telescopes swung to look. The sky answered with a kilonova, whose glow carried the fingerprints of freshly minted heavy elements. The proof arrived with quiet confidence, a signal in space-time, a bloom of light, and spectra that whispered the same story. The precious metals we prize were born in the rarest, fiercest forges the cosmos offers. Rarity is part of the truth. In a galaxy like the Milky Way, neutron star mergers may happen only once in 100,000 years. Perhaps a little more often, perhaps less, but not often. Each one, though, plants a garden of atoms, seeding space with heavy elements that drift and mix, wander and settle. Across billions of years, those atoms fold into new clouds, then into new suns and their worlds. The glitter in riverbeds, the thin threads of ore curled through rock, the deep veins we follow with lights and drills, all of it points back to collisions long before Earth had a name. Gold's charm isn't only rarity, it's temperament. It doesn't rust, hardly tarnishes, and yields easily to the human hand. We gave it meanings, wealth, promise, endurance, because it behaves so well, and because it lasts. Platinum carries its own steady grace, shrugging off corrosion, standing strong in heat, quietly useful in technology and beautiful on a finger. Their cosmic biographies give them a deeper resonance still. They are more than decoration or utility. They are messages from violent birthplaces. Wear a gold band, and you're wearing the cooled memory of two dead stars meeting after a dance that lasted longer than civilization. Other heavy elements keep similar company. Uranium and thorium, fuels that warm reactors on Earth, were lifted into being by our process tempests. Their slow decay does housekeeping in the dark, warming a planet's interior, helping tectonic plates creep and mountains rise and fall. Trace by trace, rare Earth elements that color screens and help engines and wind turbines have a lineage that runs through the same brief, blazing foundries. The modern world, from jewelry boxes to power grids, is stitched to explosions that outshone galaxies for a moment and then faded. Imagine the path those atoms took. Born in collisions that flashed brighter than whole star cities, they raced outward into the thin, dark, cooled, met dust, bonded, and drifted for eons. Some were folded into the cloud that collapsed to make our solar system. Some sank into the new Earth's crust. Some stayed near the surface. Some rode comets and asteroids. A few slipped into biology in tiny amounts, becoming part of the fine balances that chemistry keeps in a living body. The journey is long, and the patience involved is astonishing. Perhaps our fascination with gold reaches deeper than a taste for shine. Maybe there's a quiet recognition of age and distance in its gleam. When ancient people buried treasures with their dead, when partners exchange rings today, we honor a story that began far away. Matter made in brief, impossible conditions, carried across light years, stored in a planet's skin, lifted by human hands. The ornament is a witness. Its pedigree is older than mountains. Look at a coin in sunlight or a platinum setting catching a kitchen lamp. You are seeing not just value, but history. The metal was born in a crush no furnace can imitate, flew across space, joined a world, and waited, steady and patient, until someone found it. The universe has many wonders, but few so humbling as this. The precious metals are precious not because we decided so, but because their recipe requires scenes that almost never happen. Scarcity is woven into their being. When stars end, they leave more than darkness. Even in dying, they are generous. Their ashes move like weather across a galaxy, carried, stirred, and eventually gathered. Those ashes are not inert. They are the ingredients for everything that follows. New stars find their fire in them. New planets are poured from them. New oceans and rocks and living cells learn their shapes from them. Watching stardust drift is watching matter practice patience. Small stars like our sun finish gently. They swell, breathe out shells of gas, and form luminous veils we call planetary nebulae. Those shells carry carbon and oxygen and nitrogen, the quiet work from a long stellar life, out into the night. Larger stars end with thunder, hurling their insides into space with supernova shock waves. Either way, what was once locked in cores gets its freedom and begins to wander. Between stars, there is room enough for 1,000 stories. The interstellar medium sounds empty until you read the fine print. It holds atoms, molecules, and grains, thinly spread, drifting in slow currents. The density is lower than anything we know on Earth, but when you measure across light years, it adds up to a vast reservoir. Not all dust is alike. Some grains carry silicates. Some carry the signatures of carbon chemistry. Some hold heavier elements born in explosions. These specks keep the fingerprints of the stars that made them. Now and then, we find tiny, ancient grains preserved inside meteorites that fell to Earth pre-solar dust older than the solar system itself. Their isotopes tell of other suns, other histories. To hold such a grain is to hold a time capsule that predates our world by billions of years, a fragment of someone else's sky that drifted into the cloud that became ours. Dust and gas do not stay scattered forever. Gravity is stubbornly patient. It draws what's near a little nearer. It builds clumps. It lets time do the rest. Shock waves from supernovae can compress a drifting cloud until it crosses a threshold and begins to collapse. Colliding galaxies can stir gas and bring fresh raw material together. Where conditions turn favorable, dark nebulae thicken regions so dense they block starlight, lit from within by gentle warmth. These are nurseries. Inside them, knots condense. Disks spin up around baby stars, and the leftover material learns to be planets, moons, and smaller bodies. Every river and rock, every drop of rain and breath of wind, every living thing begins here, in dust, learning to settle. Think of water in a glass or flowing under a bridge. The hydrogen has been here since the universe's first minutes. The oxygen began in stars. A star once exhaled that oxygen, and the atom wandered until Earth offered a home. The iron in the planet's core, the silicon in its crust, the calcium in a shell or in your bones, they all made the long trip as dust and gas, caught in the slow circulation of a galaxy. The timing is leisurely. Gas can drift for millions of years before gathering the courage to clump. A nebula can cradle its secrets for tens of millions more before finally letting gravity light a star. After a solar system forms, it may take billions of years for life to arrive and find a foothold. None of it would happen without the quiet traffic of dust, moving like pollen on a breeze that never stops. Images of nebulae glow in familiar colors, soft reds where hydrogen sings, greens where oxygen hums, blues where hotter light peeks through. Those photographs are not just beautiful. They are snapshots of matter mid-transformation, showing how the ruins of one generation become the seeds of the next. It is a reminder that endings leave gifts, and that the universe knows how to use them. Our own system began in such a cloud, about 4.5 billion years ago. A ripple of compression passed through a patch of gas and dust, and it began to fall in on itself. The center grew hot until the sun lit. The rest spread into a disk. From that disk, Earth gathered itself grain by grain. Some stardust stayed as comets and asteroids, cold archives of beginnings. Some fused into rocky worlds and gas giants. The shapes we know now grew from the scattered remains of older stars. The process hasn't ended. Dust still wanders through the Milky Way. New clouds still thicken. New stars still kindle. New planets begin to cool. Tiny grains continue to fall through Earth's air each day, settling on rooftops and open water and quiet snowfields. You don't notice them. There is always more sky than dust, but the visitors are there, tiny envoys from distances we rarely imagine, slipping into the everyday without ceremony. There's comfort in how this cycle refuses to hurry. Stars live and close their kitchens. Their contents drift and gather. New fires start. Worlds appear. Life tries patterns, revises them, and tries again. Time stretches, matter moves, and eventually something with lungs and eyes and a mind starts asking where the atoms came from. The answer is as gentle as it is grand. They were on their way to you before there was a you to wonder. Maybe that's why the night sky feels familiar, even though it is vast beyond measure. On some soft level, we recognize the light. It's family light, made of the same kinds of atoms our bodies borrow. The dust between stars is not foreign. It is the same dust that makes mountains, shells, soil, and skin. We are not outside observers. We're participants in an old, ongoing exchange, carried along by a motion that began long before us and will continue long after. When you linger on a photograph of a nebula, or step outside and let your eyes adjust until the faintest stars appear, try a thought experiment that's more like a whisper than a lesson. Follow a gold atom backward, past the jewelry box, past the vein of ore, past the settling of a planet. See it born in a flash, when two neutron stars finally met, then sailing outward, cooling, sticking to dust, traveling for ages until its path crossed ours. Follow an oxygen atom backward through a river to a star's core. Follow iron through a blood vessel to a supernova's shock. The journeys are different, but the destination, for a moment, is us. The universe is generous with its circles. Heavy elements made in brief catastrophe become the quiet infrastructure of worlds and bodies. Precious metals made in rare collisions become symbols we press into promises and carry on our hands. Stardust made by many endings becomes the raw material for many beginnings. The traffic never really stops. It only slows down enough for things to take shape. So when a ring catches the light, notice the way it gleams like a tiny, contained sunrise. When a picture shows a cloud of gas glowing green and red and blue, see it as a nursery, not a distant decoration. When a soft layer of dust gathers on a windowsill, allow the fanciful thought that a few of those grains are older than the Sunday. You do not have to prove it to let the feeling help you sleep. Gold and platinum feel timeless because they carry time in them. Time measured in orbits of dead stars, in the length of a wave rolling through space-time, in the cooling of debris that crossed deserts of emptiness. Stardust feels intimate because it has been everything. Core and cloud, rock and rain, leaf and skin. The cosmos asks for patience and gives meaning in return. It makes its rare riches in brief, ferocious moments, and then lets them drift until some of them learn to love and to listen. If you hold such a metal, you are holding a quiet echo of neutron stars colliding. a memory of a kilonova's fireworks, a keepsake from processes that make the universe both fierce and kind. 4.5 billion years ago, this world began as a hush of dust and gas circling a young sun. No continents, no seas, only a dim swirl where gravity was learning our name. The ingredients were already ancient, forged in stars that had lived and died long before, scattered by supernovae into the wide, dark. Earth is not made of anything new. It is a careful collector of hand-me-downs, a patchwork quilt sewn from the ashes of countless stellar lives. Iron, silicon, oxygen, carbon, and dozens of quieter companions drifted in the solar nebula, felt the slow pull of gravity, and found one another until a planet took shape. To understand this place is to recognize a cosmic inheritance. At the center sits iron. In the stormy youth of the planet, everything was molten, and collisions were common asteroids and baby worlds shouldering past and sometimes striking hard. In that liquid chaos, heavy elements sank while lighter ones floated. Iron and nickel, both born in the hot cores of massive stars and flung outward upon their deaths, gathered in the deepest chamber and settled there. The result is not a cold, solid lump, but a restless engine, part liquid, part solid, churning and spinning. From that motion, our magnetic field rises, an unseen umbrella that bends the worst of the solar wind aside and helps keep our air in place. Without that shield, the story told on this surface might have been shorter, harsher, or not told at all. Around the metallic heart lies the mantle, a thick cloak of rock rich in silicate minerals. Silicon, oxygen, magnesium, and other children of stellar fusion bonded into crystals, and the mantle learned to flow at a pace too slow for eyes, but fast enough for continents to drift. From its depth came volcanoes and mountain chains, rifts and ridges, the slow rearrangement of maps. Above that, the crust cooled thin in places, thicker in others, becoming the ground we touch. A rock in the hand is condensed starlight, arranged into patience. Granite cliffs, dunes of quartz, delicate lattices that trap a flash of sunlight and give it back in sparkle. Silicon and oxygen, given enough time, learn elegance. The air above the crust was not always friendly to lungs. Early Earth breathed out a mix of carbon dioxide, methane, ammonia, and steam, a warm haze with almost no free oxygen. Still, the pieces for change were present. Oxygen, forged in long-dead stars, weighted, locked in minerals and in water. Hydrogen, older than any world, was everywhere. When tiny organisms learned to crack water with sunlight, photosynthesis, oxygen began to seep into the seas and then into the sky. At first it vanished into reactions, rusting the oceans and staining stone. Only later did it build up in the air until breathing became a possibility. Nitrogen, quiet and abundant, joined in as the soft background of the atmosphere, a gift from massive stars that broke and remade it long before there was air to hold it. What we inhale today is a blend of ancient favors, mixed and remixed by weather and life. Then come the oceans, which still surprise even as they feel familiar. Water's atoms are storytellers. Hydrogen from the universe's first minutes, oxygen from stellar furnaces. Some water likely condensed as the planet cooled. Some arrived as icy messengers, comets, and water-rich asteroids struck and melted, adding to the young seas. However it came, the result is a surface veined with blue. Each wave carries atoms that once drifted between stars, waiting for a world that could keep them liquid. The inheritance reaches into details we barely notice. Trace elements in the crust carry specific histories. Calcium, essential for bones and shells, came from stars that fused helium into heavier hearts. Potassium and sodium, the quiet electricity in nerves and muscle, were shaped in similar crucibles. Gold and uranium took rarer paths through neutron-rich cataclysms, then rode the long current into Earth's skin, where hands would someday find them. To live here is to live among heirlooms. To breathe is to use them. To move is to ask them to work together again. What sets this planet apart is not only the list of ingredients, but the way the recipe settled. Other worlds in this system received the same delivery, but the proportions and timing here were forgiving. The iron core offered protection. The silicate crust stayed active rather than locked. The atmosphere changed under the nudge of living things. The oceans made chemistry mobile. None of it was designed. All of it followed simple rules until complexity appeared. Even the violence participated. Giant impacts stirred the pot and may have given us the moon, whose steady tug tames the tilt of our spin and pulls tides across the margins of continents. Volcanic breaths thickened and thinned the air. Plate tectonics recycled elements, so the crust never fell asleep. You can feel the intimacy of it. The same iron that sinks at the center moves through you as hemoglobin, clasping oxygen and letting it go in time with your pulse. The oxygen in your lungs was forged in cores that never saw sky. The carbon stitched into muscle and memory was cast and scattered long before Earth cooled enough to hold it. The inheritance is not only geological, it is personal. Teeth and bone and breath are new arrangements of an old kit. Look up and the stars appear distant. Then look down and remember that their work is underfoot. A mountain is a monument made from star ash and heat. A river is hydrogen from the beginning of time, carrying oxygen borrowed from a sun that died and shared. Air is not emptiness. It is a mixture of gifts. Nitrogen's calm, oxygen's fire, argon's quiet, gathered from across the galaxy and invited to stay. To live here is to take part in a family story, one that began before there were families to tell it. The beauty is in the connections. Each part of the world ties to events that happened elsewhere, long ago. Iron at the center, silicon in the crust, oxygen in the air, water in the sea, all of it began as dust, as fragments of old stars set in motion by gravity and time. Those fragments gathered, warmed, and were taught to behave together until life could try its hand at complexity. Bare feet on soil, a glass lifted to the mouth, a clean breath taken after rain, each is a way of touching what stars have left behind. Water deserves its own quiet astonishment. It pours and freezes, climbs roots and turns mills, rests in clouds and in cells. It is so ordinary that we forget how strange it is. At heart, it is a marriage between the simplest atom and a more elaborate one. Hydrogen, single proton lightness from the universe's dawn, and oxygen, a latecomer forged in the depth of stars. When those pieces met, they made a molecule that turned chemistry into a conversation. What makes water remarkable is not that it exists, but how it behaves. It is the best listener among liquids, dissolving more kinds of substances than any other. Sugars, salts, amino acids, water receives them and lets them mingle. This is what metabolism needs, a place for molecules to meet, react, and part. Without that welcome, life's early steps would have stalled. Water also refuses to follow the usual rules of freezing. Most materials become denser as they solidify. Water swells a little, so ice floats. Lakes freeze from the top, leaving liquid beneath where fish and plants can wait out winter. If ice sank, many waters would freeze solid, and spring would come to empty basins. This quirk is a gift of geometry. The bent shape of the water molecule locks into an open lattice when cold enough, and the lattice rests lightly on the liquid below. Another kindness is water's high heat capacity. It takes real energy to change its temperature. Oceans smooth the swing between day and night, summer and winter, softening climates so life can settle into routines. Without that thermal buffer, days might scorch and nights bite, and storms might rule too often for calm to gain ground. As for where Earth's water began, no single account holds all of it. Some condense close to the sun, some arrive from colder reaches, some may have been stored in minerals and released as the planet exhaled. The important part is that water is not local in spirit. Wherever hydrogen and oxygen are common and conditions are kind, water appears. We have seen its signatures in clouds around other stars, in the thin airs of far-off worlds, in plumes that burst from the icy skins of distant moons. It seems that when the universe has the pieces, it tries this trick again and again. If water flows elsewhere, perhaps the chemistry that enjoys its company flows too. Here, water is folded into every process. It climbs xylem in trees and returns through stomata as mist. It travels our veins, carrying food and carrying waste. It shapes valleys and coasts, carves canyons, rounds stones. It cycles evaporating from sea, drifting into sky, condensing into rain, seeping into soil, running back to the ocean. Every drop has a long resume: glacier, cloud, creek, cell, tide, breath. The glass on your table may hold molecules that once fell as snow on an ancient plain or warmed a dinosaur's blood. There is a soft poetry in how it links us to the past. Hydrogen born with the universe, oxygen born in stars, a bond formed in the quiet between. Each sip is a bridge between first minutes and last breaths, between stellar death and human conversation. Rivers gave paths for travel and for grain. Oceans carried boats and ideas. Cities grew where water paused and invited people to pause with it. Our dependence is complete biological, social, and cultural, and behind it lies a coincidence written by physics. The shapes and charges of two elements allow a liquid so useful that we learn to tell our history along its edges. The search beyond Earth often starts with a simple instruction: follow the water. Where water is liquid, the odds feel richer. That is why dried deltas on Mars invite careful looks, and why the secret seas of Europa and Enceladus hold our attention. If chemistry is going to gather itself into something that persists, water is the stage it prefers. Nothing about water is ordinary when you look closely. Its ubiquity is the miracle. It dissolves, stabilizes, and flows. It buffers heat, carries charge, and shapes landscapes. It turns two widespread elements into something more than the sum of their parts. Pour a glass, and you pour a timeline. The hydrogen has been here since almost the beginning. The oxygen spent ages locked in stellar cores, and then in stone. Together, after long travel, they have become the solvent that lets your body work and your mind stay clear. What seems plain is a rare kind of perfection, tuned enough to carry the story forward for billions of years more. This world is not simply a place. It is a gathering of star-made elements, of accidents that turned into patterns, of water that learned to carry life's cargo. The core hums, the mantle flows, the crust drifts. The air breathes, the oceans keep time. Each part owes itself to events that happened far away and long ago. And yet here they are, arranged into a home where lungs fill, seeds open, and questions arise. Bare feet on ground, a swallow of cool water, a patient exhale at night, each is a way of touching the vast family story we were handed. Each a way of hearing the quiet truth beneath the noise. The stars are not only above you, they are within you, around you, and beneath your feet, still giving what they gave at the beginning. You carry a quiet cosmic history, written not in ink, but in atoms. When people say we're made of stardust, it isn't metaphor, it's a plain, astonishing fact. The elements that shape a heartbeat and brighten a thought were forged in stars, flung into space, and gathered back into the chemistry of life. Calcium hardens bone, iron ferries oxygen, carbon builds and binds, oxygen feeds the flame of metabolism. To meet your eyes in a mirror is, in a small and tender way, to watch the universe consider itself. Begin with carbon, the scaffold of biology. Every cell leans on carbon's easy grace, 4 steady bonds that can reach in different directions, letting atoms lace into chains, close into rings, branch into frameworks. Carbon backs the spiral staircase of DNA, links amino acids into proteins that fold and work, and fashions sugars and fats that store and spend energy. None of this would exist without an earlier choreography in stars. The triple alpha dance, where 3 helium nuclei met under crushing heat and pressure to become carbon. The carbon in you once drifted as a cinder from a dying star, cooling in the dark until a world and a body were ready to use it. Think of oxygen, the element of breath. With each inhale, oxygen slips from lung to blood, clings to hemoglobin, and rides the current to your cells. There it helps unspool energy from sugars, keeping you warm and awake. Oxygen is threaded through water, proteins, lipids, and nucleic acids. It is the second most abundant element in the body. Its story runs through stars more massive than the sun, where carbon captured helium to become oxygen. When those stars ended, their oxygen spilled outward, some into oceans and air, some into you, sometimes bound with hydrogen, as the water that moves through every tissue, sometimes as the O2 that leaves again with each unhurried breath. Iron adds a dramatic link. In hemoglobin's center sits an iron atom, a patient clasp for oxygen. Without it, lungs would fill, yet cells would starve. Iron is the limit of ordinary stellar fusion, the quiet full stop where energy can no longer be earned by building heavier nuclei. To make iron in great supply requires collapse and shock supernovae, and the iron in your blood is a relic of such an ending. Each beat of your heart is powered, in part, by the ashes of a star. Calcium lends strength, first to shells and limestone, then to skeletons. It forms in the late lives of massive stars and takes to space in supernova winds. In your body, it crystallizes into bone, a living mineral scaffold that lets you stand, reach, dance, repair. Phosphorus is rarer but essential. It links DNA's backbone, stores and releases energy in ATP, the rechargeable coin of the cell, and pays for every neuron signal. Its path also runs through massive stars and explosive endings. Every idea, every memory, carries a trace of stellar accounting. Potassium and sodium deserve a soft spotlight. Their careful imbalance across cell membranes lets electrical whispers travel. A fingertip flinches, A heart keeps time. A dream ripples through the night because these ions born in stars move when and where they must. Even the trace elements carry ancestry. Zinc steadies enzymes, copper lends a hand in blood chemistry, iodine guides hormones, magnesium is the quiet partner in hundreds of reactions. Some rose in steady stellar fires, others in neutron-rich tempests. Their amounts in you are small, their importance is not. What's striking is how readily the periodic table offers tools for life. Carbon supplies structure without fuss. Oxygen fuels reactions, while water keeps them gentle and mobile. Iron holds and releases breath. Calcium builds load-bearing lattices. Phosphorus manages energy, while potassium and sodium pass messages. Biology did not invent these properties. It borrowed them. Life is the art of repurposing stardust with care. Kinship follows from that borrowing. You share elements not only with every person you meet, but with maple trees and moon snails, with rivers and rust. The calcium in your teeth echoes in a clam's shell. The iron in your veins rhymes with Earth's core. The oxygen that fills your chest also brightens flame and weathers stone. We are variations on one theme, arranged differently, made from the same small kit. It's easy to feel small under a wide sky. This story offers a gentler frame. You are not outside the cosmos, peering in. You are of it. Old explosions made possible this breath, this step, this thought. Your pulse is the after music of stars. For a long time, the stars kept their compositions secret. They were bright and distant, good for calendars and stories, but unreachable to hands and scales. Early seekers worked as alchemists, part experiment, part dream, trying to turn base metals into gold and to find an elixir for a longer life. Their recipes mixed hope with heat, and while the legends didn't hold, their patience with furnaces and flasks laid paths toward chemistry. The world still seemed to be built from four ancient notions: earth, air, fire, water qualities and essences more than atoms. The turn came with the scientific revolution. In the 1600s, Robert Boyle argued that substances could be broken down into more fundamental parts, elements shifting the conversation from qualities to constituents. In the 1700s, Antoine Lavoisier weighed reactants and products with calm precision, showing that matter is conserved and drafting a first clear list of elements. Chemistry had a foundation. Ingredients could be named and counted, but the heavens were still out of reach. No one could bottle starlight until someone learned to read it. Spectroscopy became the translator. Heat an element, and it will emit or absorb light at very particular colors, leaving a pattern of lines as unique as a fingerprint. In the early 1800s, Joseph von Fraunhofer noticed dark lines crossing the sun's spectrum, missing colors without yet knowing their cause. A few decades later, Gustav Kirchhoff and Robert Bunsen matched laboratory spectra to those gaps and found a key that fit the lock. Sodium makes twin yellow lines. Hydrogen lays down a set of red and blue-green marks. By comparing those fingerprints to the sun's, they showed that the same elements we know on Earth live in the sky. The old divide between celestial and terrestrial matter softened and fell away. The periodic table wasn't just a catalogue of earthly stuff, it was a universal ledger. Spectroscopy kept delivering surprises. In 1868, during a solar eclipse, astronomers saw a spectral line that matched no known element. They named the stranger helium, after the sun itself. Only later was helium found on Earth, a reversal that reminded everyone how much the sky still had to teach. In the 1,920 seconds, Cecilia Payne, studying stellar spectra with care and courage, showed that stars are made mostly of hydrogen, with helium next, overturning the assumption that they share Earth's heavy composition. Her result was doubted, then confirmed, and now sits at the center of astrophysics. Stars are hydrogen furnaces. Linking the periodic table to the lives of stars came next. In the 1950 seconds, a team, Margaret Burbidge, Geoffrey Burbidge, William Fowler, and Fred Hoyle, assembled a grand picture. Elements are made in stars by fusion, in supernovae, by shock and neutron capture, in other rare events where the rules allow. Their work tied carbon's triple alpha birth, oxygen's helium captures, iron's stoic limit, and the R-process torrent that builds gold and uranium into one patient story. The detective tale of Starlight reached an elegant chapter ending. The atoms in our bodies carry well-kept records of where and how they were forged. Since then, the reading has grown more refined. Telescopes now split the light of galaxies across billions of years, mapping how element abundances change as generations of stars live and die. Spectra reveal the breath of newborn stars in dusty nurseries, the weather of exoplanet atmospheres, the ashes of supernovae, the glow of kilonovae, where neutron stars collide. Each line is a clue. Each shift in color is a whisper from matter across the void. The sun is roughly 93 million miles away, and yet a prism can make its composition as legible as a solution in a beaker. Light leaving a distant star centuries ago can tell you, tonight, what was present when it began its journey. The universe leaves fingerprints everywhere. We only had to learn to look. The path from alchemy to spectroscopy is a lesson in curiosity's quiet strength. The dream of turning lead into gold gave way to the recognition that gold itself comes from rare cosmic violence. The old elements, earth, air, fire, water, stepped aside for hydrogen, helium, carbon, and oxygen, and the realization that these atoms are not parochial. They are shared. They belong to stars and stones and skin alike. All of this returns, gently, to you. Your calcium is a hand down from massive stars. Your iron remembers a collapse. Your phosphorus once rode a shockwave. Your potassium and sodium keep a signal moving in the dark. Hydrogen in your water is as old as time itself. Oxygen in your breath was made hot and hard in places no wind ever blew. You are not beside the universe. You are a local arrangement of it, thinking. The next time you feel your pulse settling into evening, or your chest rise and fall in a quiet room, consider the journey your atoms took to get here. Carbon learned patience in a core that never saw sky. Iron was born in a flash and thrown outward. Oxygen flowed from a star's last gifts to a river's surface to your lungs. You are a mosaic of remains and beginnings, a memory of stars with new work to do. And when you step outside and the night opens, let the light overhead be more than decoration. It is a message. Every point declares itself in lines and colors a spectroscope can read. Humans learn that language and, in doing so, learned what we are made of. The distant became familiar. The cold became kin. The universe, which once seemed indifferent and far, now sits gently in your chest, breathing with you, telling its story softly, atom by atom. The heavens and the earth are not strangers to one another. They're written in the same alphabet, small, sturdy letters called atoms, and starlight is the lamp we use to read the script. The universe does not waste. Once matter comes into being, it doesn't vanish. It changes costumes. It drifts, gathers, burns, cools, shatters, and returns, moving through a long circulation that has been turning for billions of years. That quiet recycling explains why galaxies keep kindling new stars, why planets can rise from dust, why oceans gather and living things learn to breathe. Without this continual reuse, the cosmos would harden into silence. Instead, it breathes, renewing itself with each generation. In the beginning, the pantry was simple: hydrogen and helium, with just a whisper of lithium, flowed in vast cold clouds. Gravity drew those clouds inward, and the first fires began. Inside those fires, stars' new elements were forged. When the fires aged and faltered, they let go of what they had made, and those gifts scattered into the dark. From the mix, new clouds formed, fell inward, and lit again. The cycle looped on. Every atom in you has traveled this slow carousel at least once, probably many times, before arriving in your hands and heart. Galaxies are the great rooms where this work unfolds. In their spiral arms and central swells lie nurseries nebulae, dense with gas and dust. Some glow in soft reds and greens, lit from within by newborn stars. Others hide in darkness, so thick with dust that light slips around them. There, hydrogen finds partners, carbon tries on new arrangements, tiny silicate grains take shape. Gravity kneads the mixture until knots form. In the dense centers, stars ignite. Their light and winds sculpt the surrounding cloud, sending ripples that nudge other pockets to collapse. One generation helps usher in the next, each birth rearranging the cradle it came from. The lives of stars are varied. Small ones sip their fuel and can glow for trillions of years, steady and frugal. Big ones blaze through their reserves in only a few million years, living brightly and ending fiercely. By whatever path, every star returns part of itself to the galaxy. The smaller exhale their outer layers, leaving soft shells of gas that drift away as planetary nebulae. The massive end as supernovae, flinging heavy elements in all directions. Even what remains white dwarfs, neutron stars, black holes shapes the flow, tugging on nearby matter, stirring or steadying the neighborhood. Each generation adds to the pantry. The earliest stars could only kindle helium from hydrogen, and then, with time and pressure, craft carbon and oxygen. Later generations inherited those elements and built heavier ones, silicon, iron, and beyond. By the era our solar system formed, the gas cloud that birthed it had been enriched by countless cycles. That's why Earth is not a helium balloon adrift in space, but a complicated world with rocks and rain, roots and bone. The recycling isn't only inside stars. Whole galaxies breathe. Stellar winds and explosions can push gas outward, even into intergalactic space. Gravity gathers it back, sometimes long after, feeding fresh waves of starbirth. When galaxies approach and merge, their clouds collide and compress, and newborn stars arrive in brilliant clusters. The Milky Way and Andromeda will meet in a few billion years. Their matter will fold and mingle, and a new galaxy will grow from the shared inheritance. Continuity is everywhere. The oxygen you draw in tonight may once have warmed the surface of a star older than the Sunday. The calcium in your bones may have drifted for eons as dust, circling nowhere before settling into the cloud that became Earth. The iron in your blood might have been hammered into being by a shockwave far away and long ago. Elements play many roles across time: part of a star, a stone, a river, a body, then ash, again, then cloud. Even dust matters. Tiny grains, smaller than smoke, carry coats of water, ammonia, carbon monoxide, thin frostings laid down in cold clouds. They bump and stick, building little clumps. Over long stretches, those clumps grow into pebbles, then boulders, then planetesimals, the seeds of planets. The dust you wipe from a windowsill is made of humbler stuff, but the gesture echoes the same logic. Small pieces learn to join, and from that joining, something larger begins. Cosmic recycling is both fierce and tender. Supernovae tear stars apart with energy beyond reckoning. Their ashes drift like pollen. Black holes swallow, yet their jets can push and heat galactic gas in ways that regulate when and where stars form. Collisions and calms, violence and stillness together, they keep matter from sleeping too long in one form. Destruction resets the board, so renewal can proceed. Life leans on this cycle. Without repeated generations of stars, there would be too little carbon for cells, too little oxygen for breath, too little nitrogen for the gentle alchemy of proteins and DNA. Without supernovae, calcium for bone would be scarce, phosphorus for energy storage rare, iron for blood in short supply. Without icy messengers, comets, and water-rich asteroids, our world might have stayed dry. What feels ordinary stone, stream, leaf, hand, is the end of many passages and the start of many more. Astronomers sometimes call this a middle-aged universe. Enough cycles have passed to enrich galaxies with heavy elements, but gas and dust still abound. New stars continue to arrive. Far ahead, the raw materials will thin, star formation will slow, galaxies will drift into quieter habits. For now, the breathing continues. Inhale, exhale, gather, release, kindle, dim. There's comfort in the rhythm. The atoms that burned once as starlight now shimmer in crystals, flow in rivers, and time your pulse. Nothing is truly lost. Everything transforms. Look up at the Milky Way as it arches across a clear night. It is not a static stripe. It is a living workshop, a broad, slow motion of making and unmaking. The bright points you see are stars in their long middle chapters. Around them, dark clouds are forming the next episodes. The galaxy breathes, the universe renews, and you are folded into the breath. Time moves through this story like a quiet river, hard to hold and easy to notice only by what it leaves behind. Trees keep rings, faces keep lines, stone softens into sand. In the cosmos, time is recorded in subtler ways. Atoms carry clocks within them, some that tick by light, some that tick by decay, letting the universe keep its own ledger. We learn to read these clocks, and with them we learned how old things are and how long they've been practicing their roles. Radioactive decay is a steady metronome. Certain isotopes, versions of elements with extra neutrons tucked into their nuclei, are unstable and will, given time, fall into more comfortable arrangements. Each kind has its own pace, a half-life, the time it takes for half a sample to transform, whether buried in rock, locked in a meteorite, or floating in interstellar dust. These clocks keep their rhythm, indifferent to weather and worry. Carbon-14 is the familiar one. High in the air, cosmic rays nudge nitrogen into becoming radioactive carbon. Plants take it in, animals eat the plants. And while a creature lives, the amount of carbon-14 inches it stays, roughly matched to the air. When life stops, the exchange stops, and the clock starts. Carbon-14 decays back toward nitrogen at a known pace. by measuring how much remains, we can date wood, bone, cloth for tens of thousands of years, long enough to place old campsites on a calendar and to let forgotten stories find their order. For deeper time, other clocks keep watch. Uranium-238 changes into lead with a half-life close to the age of Earth. Tiny crystals called zircons can trap uranium when they form and resist leaking for ages. By checking how much uranium has become lead, geologists learn when those crystals cooled. The dates cluster around 4.5 billion years for the oldest terrestrial minerals, and meteorites tell the same tale for the birth of the solar system. Thorium, potassium, rubidium, each offers a different tempo. By comparing them, scientists cross-check their readings, building a timeline sturdy enough to hold mountain ranges, volcanoes, oceans rising and falling. These clocks reach beyond our planet. Some old stars hold traces of uranium and thorium in their light. By comparing those long-lived isotopes to stable neighbors, astronomers can estimate how long it's been since those atoms were forged, numbers that point to ages around 12 or 13 billion years for ancient stellar populations. The clocks do not give exact birthdays, but they sketch the centuries in broad, honest strokes. Other isotopic systems, strontium, neodymium, record the chemistry of how planets differentiate into core, mantle, and crust. Read carefully. They tell you not just when a world began to cool, but how it learned to separate itself into layers, how its surface fed back on its interior, how continents gathered and wandered. Even light keeps time when paired with decay. In some supernovae, freshly made nickel 5-6 decays into cobalt, then into iron. The energy from those steps powers the fading glow weeks after the blast. Astronomers watch the afterlight dim and compare it to the known rates of decay, learning about the mass ejected, the energies involved, the way the explosion unfolded. The brilliance overhead is, in part, the visible face of ticking atomic clocks. The oldest clock is softer still, the cosmic microwave background, a faint wash of light from when the universe was young and hot. Its subtle patterns, paired with the measured expansion of space, point to an age near 13.8 billion years. That number is checked against the oldest star clusters, the slow decay in ancient stars, the chemistry of primordial gas. The agreement is a kind of harmony, a sign that the clocks keep time together. What makes these clocks calming is their impartiality. They don't heed our schedules. They tick in caves and in comets, in zircons, and in the glow of dying embers. They remind us that time is layered and long, and that our days lie lightly across deeper ages. And they are not only far away. Potassium 40 inches, your own body decays very slowly. You carry a mild, harmless clock within you. Even now reading, resting there is quiet timing in your bones. The same physics in you as in a meteorite or a mountain. There is poetry in the continuity they reveal. Uranium in granite, carbon in bone, thorium in an old star. They're all telling parts of one story. Each isotope is a little timepiece wound long ago and still running. Without them, much of the past would blur. With them, we can place events in order, find beginnings and endings, and see how pieces connect. When you imagine time, you may think of hands circling a face, or pages turning on a calendar. The deepest measures live in matter. Every atom has a background, and some remember it well enough to share. Hold a zircon between finger and thumb, and you cradle a note from the hot youth of Earth. Split the light of a star, and its spectrum becomes a receipt for what it contains, and sometimes for how long it has held it. The answers to how old are not all written in the sky. They're also in the pebbles underfoot and the small, steady currents in your chest. Long before glass lenses and mirrored domes, before the quiet names of protons and neutrons were whispered into classrooms, people stood under the sky and tried to make sense of what everything was made of. The sea that gave and took, the soil that held roots and bones, the flames that warmed and frightened, each demanded a story. Without spectrometers or particle accelerators, cultures wove explanations from the materials they could touch and the patterns they could feel. Fire, air, water, and earth became more than substances. They became sacred forces, spirits with character and mood. Those early stories were not mistakes so much as first drafts, poetic sketches of the same grand recipe that science patiently writes in finer script. Fire felt alive. It ate wood and breath, released smoke, danced and vanished without a trace. To the Greeks, it was a fundamental. Heraclitus saw an ever-living fire at the heart of things, a principle of change that kindled and dimmed in measure. In Zoroastrian temples, fire stood for truth and clarity. In many myths, it was a gift stolen from the high places Prometheus, slipping a coal into human hands, a defiant spark against the dark. The idea that fire was elemental made sense when its heat saved lives, and its hunger demanded respect. To watch a flame was to watch transformation. How could it be anything but basic? Water carried equal weight in imagination and need. Rivers fattened fields and then, sometimes, took them back. The Nile's pulse wrote a calendar on Egyptian shores. Across traditions, a great, encircling river or primeval ocean cradled the first beginnings. In Hindu cosmology, creation rises from cosmic waters. In Norse telling, icy mists and rivers feed the first stirrings in a yawning void. Water was a womb, a memory of the deep. It softened stone, mirrored the sky, and entered every living body. If an element is something you cannot live without, water wore the title easily. Air was quieter, but never absent. It was breath and wind, spirit and weather felt on the skin, needed in the chest, seen in the bend of grass. In Chinese thought, qi threaded the world, a breath-like vitality. In Old Greek and Hebrew speech, wind and spirit shared one word. To inhale was not just physiology, it was a kind of shared participation. No one could see air in itself, but everyone could see what it did. Even without instruments, people sensed a common medium moving through lungs and leaves, a hidden partner that made voice and life possible. Earth felt like certainty. It held the weight of steps and houses, stored seeds and water, lifted mountains. Cultures gave it names and faces: Gaia, Pachamama, Prithvi, mother sources that nourished and endured. Soil had character, stone held memory. You could taste clay and know a place. To call earth an element wasn't simply to label dirt. It was to honor the patience of the ground beneath every story. These four, fire, air, water, earth, became pillars in many systems. Empedocles imagined them eternal, blending and parting under the sway of love and strife. In China, a different but kindred set wood, fire, earth, metal, water spoke not only of matter, but of seasons, medicine, music, governance. Elements were more than ingredients. They were metaphors that mapped change and balance. What is striking, viewed from a quieter, later vantage, is how these mythic frameworks rhyme with the scientific impulse to simplify. People sensed that variety must hide a small set of basics. If rain, growth, storms, and decay are many faces, perhaps there are a few deep bones underneath. With time, the stories grew tools. Democritus imagined indivisible atoms, a guess that waited 2 millennia for experiments to catch up. Alchemists, half craftspeople and half poets, kept curiosity alive. They searched for elixirs and transmutations, but they also measured, distilled, recorded. Slowly, measurements hardened into methods. The old 4 faded from physics, yielding to a periodic table whose squares felt less like spirits and more like precise, repeatable realities. Yet the spirit of the search, the desire to know the recipe, never left. The echoes linger in how we speak. We still call a steady friend, grounded, borrow, fire, to name fierce ideas, speak of storms, of feeling and breath as calm. The old elements persist as metaphors because they mapped human experience onto the world in ways that still ring true. Science did not erase them, it translated them. Fire is chemical reaction, oxygen joining fuel, energy freed as light and warmth. Water is a molecule, 2 hydrogens from the universe's dawn, clasping an oxygen made in stars. Air is a blend mostly nitrogen, with oxygen and whispers of argon and carbon dioxide, tuned just enough to carry flame and breath without tipping into chaos. Earth is not one thing, but a mosaic. Silicates and metals, crystals and clays, all with pedigrees that run through stellar cores and supernovae. Far from shrinking wonder, these details deepen it. The modern revelation is not colder, it is more intimate. Stars are the true hearths, where light is minted and heavier elements are cooked. The galaxy is an ocean of gas and dust with currents, tides, and hidden nurseries where new suns rise. The very air we use travels in a galactic loop, born in furnaces, scattered by winds, gathered into worlds. The ground is stardust, compacted and arranged until roots can take hold. The myths weren't literal, but they intuited a unity. The elements within us and around us connect to a larger whole. Culture and science, rather than rivals, look like partners who arrived at the same table by different paths, one bringing meaning, the other measurements. When an elder story says the world is fire, air, water, and earth, it ties us to the cosmos with symbols. When a lab says we're carbon, oxygen, calcium, iron, it ties us to the cosmos with spectra and numbers. Both insist we belong. Hold that belonging and entertain a thought experiment in the dark. Let the universe begin as it did, hot, bright, expanding, and then imagine it never learned to make stars. There are no points of light scattered through night, no suns to warm any orbit, no galaxies glittering like spilled jewels. Only hydrogen and helium drift forever, thin and patient. At first, such a cosmos sounds peaceful, a quiet sea without storms. Sit with it a little longer, and a different truth emerges. Without stars, the universe would be unrecognizable. Stars do not merely decorate the sky, they are engines of change. The young cosmos knew hydrogen, helium, and a trace of lithium. That was the whole pantry. Only when gravity squeezed clouds and lit the first cores did fusion begin to knit heavier elements. Carbon, oxygen, nitrogen, silicon, iron. If stars never formed, the periodic table would stall at entry 3. No carbon for chains and rings. No oxygen to breathe or bind with hydrogen into water. No silicon to craft rock. No iron to anchor cores or carry oxygen in blood. Chemistry would be thin and timid. Molecules that make DNA and proteins could not assemble. Water would remain a dream, because oxygen never arrived. The universe would have mass and motion, but not the kind of complexity that makes mountains, oceans, or mines. Structure itself would falter. Gravity might still tug gas into clumps, but with no fusion to push back against collapse. Those clumps would either drift as cold, dark clouds or fall inward into black holes without the luminous drama we see in our sky. Galaxies as bright, patterned islands would not exist. The web of light that maps our telescope's images would be replaced by a dim, nearly featureless fog laced with invisible matter. For any hypothetical observer, if such a someone could exist, there would be no constellations to connect, no Milky Way band to arch overhead, no changing positions of planets, because planets would never form. Night would not be night as we know it. Darkness is contrast, and there would be no starlight to set it off. The cosmic microwave background, the afterglow of the first fire, would be the brightest feature forever, slowly cooling and fading as space stretched, never followed by the sparkle of galaxies or the warm, steady hum of a nearby sun. Worlds need heavy elements, and heavy elements require stars. Without carbon and oxygen, even the atmospheres of gas giants would be different. Without silicon and iron, no rocky surfaces could rise. There would be no landscapes, no weather as we know it, no erosion, no soil. The idea of standing anywhere would lose meaning because there would be nothing to stand on. Beauty itself, in its familiar forms, would be absent. Sunsets, auroras, the sheen of leaves, the glitter of snow, all are starlight collaborating with matter. Without stars, color has no partner. The stage lacks actors. The canvas never meets paint. One might ask whether black holes could take up the role of creators. In our universe, black holes sculpt their surroundings, jets flashing, disks blazing because they live among stars and gas shaped by stars. Strip away the stellar context, and a black hole becomes a silent drain, pulling in what drifts by, offering little in return. Complexity needs gradients, feedbacks, cycles. Stars supply those. Without them, even gravity's drama grows spare. Time changes, too, when stripped of stars. We mark cosmic eras by stellar births and deaths, by the metal-rich generations, by supernova punctuations. Remove those markers, and time flattens into a slow expansion and cooling with little to distinguish one epoch from another. There would be no standard candles to measure distances, no clusters aging, no stellar clocks to read. The universe would pass its seasons without seasons. Life would not simply struggle. It would lack the alphabet to spell itself. Carbon, nitrogen, oxygen, phosphorus, iron vital letters would be unwritten. Without oxygen, water cannot form. Without water, chemistry loses its favorite solvent. Without solvents and elements, cells cannot begin. The universe would be silent not because ears were absent, but because no voices ever could arise. Even the subtle animations we take for granted are gifts of starlight. The wind that combs a field, the tide glinting, the green that drinks sunlight, each is a negotiation between a star and a world. Without stars, physics still proceeds. Gravity gathers, particles collide, the cosmos expands, but the poetry of interaction dims. Hydrogen atoms would meet rarely to make thin wisps of molecular hydrogen, fragile and fleeting. Over unimaginable spans, everything would cool toward an empty hush near absolute zero. The story, if we could call it that, would be one of stillness, not unfolding. This stark exercise makes our universe feel more precious. With stars, the cosmos learned to cook. It recycles, enriches, scatters, and gathers, making new chances from old endings. Galaxies shine and stir. Worlds take shape and exchange heat and light with their suns. Chemistry becomes adventurous, and somewhere, eyes open and ask questions. Strip away stars, and the richness collapses. Hydrogen and helium are admirable in their simplicity, but they need stellar fire to become forests and fingerprints. So when night clears and you can see a scatter of lights, whether a handful through city haze or a river of them where the sky is dark, pause and imagine absence. Imagine no guides for sailors or calendars for farmers, no glow at dawn because there is no sun to rise, no blue to hold birds aloft because there is no air to build, no rock to warm underfoot because there is no rock at all. That is the universe we avoided by allowing gravity to gather and stars to ignite. Instead, we live in a cosmos with kitchens. The first sparks taught matter to be more than it was, and from those lessons came planets, oceans, trees, and minds that puzzle and laugh and grieve and sing. The old myths were right in a way that matters. The world is unified. The elements we touch and the ones we are share one ancestry. Fire's warmth, water's flow, air's breath, earth's steadiness, each has a page in the scientific ledger and a chapter in the human heart. The modern story adds detail: fusion furnaces, periodic tables, spectra, and clocks set in atoms. But the refrain is the same. We belong to a universe with a recipe, and stars are its careful cooks. If you listen closely, you can hear the ladle against the pot, quiet, steady, generous, turning hydrogen and helium into everything that can hold a memory. Tonight, the universe feels lively lanterns of starlight strung from one horizon to the other, nurseries glowing in soft colors, and distant thunderheads of supernova spreading fresh elements like seeds. It's tempting to trust this brightness as a permanent mood, a forever spring of making and remaking. Yet we are living in a particular season. The cosmos is generous now because its kitchens are still stocked and its fires still burn hot. This is a middle chapter, not the epilogue, but not the prologue either. A golden hour when the recipe is still being written in the language of light. Long ago, the pace was wilder. 10 billion years in the past, galaxies were everyone's bustling neighbor, crowded with gas and eager for ignition. The first generations of stars churned out carbon and oxygen that the next waves folded into more complicated work. Since then, the raw hydrogen has thinned. Stars still arrive, but fewer each year by the cosmic calendar. The trend is gentle yet steady. Clouds become modest. Fires start more rarely. And the average night grows fractionally quieter. It won't stop abruptly. It will taper, like music slipping toward a softer refrain. As fewer stars are born, fewer new elements are minted. No furnace lasts forever, and every furnace needs fuel. Elements heavier than iron require special storms, supernova shock fronts, neutron-star collisions to appear. Those storms depend on stars being plentiful enough to live full lives and die loudly. When the birth rate fades, the universe's metalwork slows with it. The atoms we already have remain. They drift, gather, and join new shapes. But the output of fresh carbon for future forests, new oxygen for future seas, and new iron for future cores begins a patient decline. The great foundries won't close in a clang. They'll dim by degrees until the last spark is rare enough to make headlines across a galaxy of quiet listeners. The stars with us now will keep their own schedules. Blue giants, too hot, too grand, will burn quickly, and bow out in supernova flashes, scattering the last generous handfuls of heavy elements into their neighborhoods. Suns like ours will swell and blush into red giants, exhale their outer layers as gauzy shells, and settle as white dwarfs' cores left to glow, cooling slowly, steadily, stubbornly. The smallest stars, the red dwarfs, are the true misers. They sip hydrogen the way a desert plant sips rain. Their lives stretch into trillions of years, outlasting every famous star in tonight's sky. In a far future where each bright point is precious, red dwarfs will be the last hearths still warm. Imagine that epoch. The sky won't end, it will thin. The glamour of big, short-lived stars will have passed. The air of the night will be peppered with faint, long-lived embers. Supernovae will change from common punctuation to rare accent marks, centuries or millennia apart, even across volumes of space, vast beyond imagining. With few explosions to stir and seed the medium, the circulation of matter will slow. Dust will still drift, gravity will still coax clumps into being. But the spark that teaches clumps to shine will arrive less and less often. The cosmic weather turns calm. Eventually, even the patient fires go out. White dwarfs surrender their last warmth. Red dwarfs, after trillions of years of careful accounting, use up the final coins of hydrogen in their cores and settle into dark relics, black dwarfs that radiate only the faintest ghost of heat. Neutron stars chill. Black holes remain, their presence felt more than seen, like deep wells dug into the fabric of space. This isn't a universe of nothing. It's a universe of leftovers. Planets wandering without suns, cold husks circling faint embers, elements locked inside rock and ice. The periodic table still exists, but no new entries are being added to the ledger by fire. The cookbook becomes an archive. Distance lengthens, too. Expansion keeps pushing galaxies apart, and the acceleration we measure today promises an ever-widening quiet between them. Each galaxy becomes an island with fixed supplies, a pantry that won't be restocked from the outside. Within those islands, the last starbirths flicker out. Chemical diversity doesn't vanish. It simply freezes in place, a gallery of what was possible when the ovens were on. There are whispered possibilities beyond the easy reach of imagination. Perhaps degenerate remnants will occasionally collide and reignite small fires. Perhaps, on scales beyond any calendar we keep, even protons may decay, letting matter evaporate a particle at a time. Those speculations live at the edge, where physics turns shy. What's clear within any reasonable horizon is more modest. The great era of element making will slow and, for practical purposes, end, not with a curtain, but with a long diminuendo. To live while the music still swells is a gift edged with ache. It says we occupy a fortunate slice of time, not so early that the universe is mostly hydrogen and patience, not so late that the cupboards are bare and the lights going out, the ovens hum, nebulae keep their soft bloom, planets condense. Chemistry is bold enough to attempt life, and life manages sentences, songs, and long, thoughtful silences. Finite doesn't mean hollow, it means precious. The knowledge that the recipe will one day be complete sharpens the flavor of what's on the table now. The future will be a museum of atoms. Carbon will continue to tell of triple alpha moments in the bellies of stars. Oxygen will carry the memory of helium captures. Iron will remember supernova cores. Gold will carry the echo of neutron stars clapping together. Even when no stovetop glows, the cookware on the shelves will explain how the meals used to be made. Planets will orbit remnant stars for ages upon ages. Some worlds will be swallowed by black holes. Some will break free and wander, cold pilgrim spheres, counting time by collisions and close calls. Dust will still trace thin paths, but without a spark to teach it color, it will stay dust. Back here, under a lively sky, the story bends quietly toward us. We are not spectators pressed against the glass. We are the glass, the light, the room, the breath fogging the pain. Hydrogen from the first minutes, helium from the first hours, and everything beyond forged later in stars. These gathered, cooled, met in the right proportions, and tried an experiment called life. The inventory in your body is a ledger of that long work. Oxygen fills most of your mass, mostly in water, which ferries and cushions and dissolves. Carbon frames every data structure in you: DNA, proteins, lipids, sugars, make, store, signal, repair. Hydrogen, ancient to the point of myth, perches in nearly every molecule that matters. Nitrogen stitches strands and helps build shapes. Calcium holds the architecture steady. Iron carries breath where it's needed. Phosphorus speaks the language of energy. Sodium and potassium move whispers along nerves. Trace metals add fine-tuning to countless reactions. None of them new, none of them yours forever. All of them borrowed from old fires and promised back to futures we will not see. It's one thing to recite this, it's another to feel it, a weightless gravity tugging on how you think of a life. The oxygen in your lungs may have spent eons drifting as vapor in a cold cloud. The calcium in your teeth once lay in a star that lived and died before our sun lit. The iron in your blood remembers a blast. Every inhale, every sip, every bite is an exchange with a history. You are complicated not because you invented complexity from scratch, but because you inherited a box of parts that had been field-tested in many stars, many times. Patience runs through the recipe like a quiet river. Stars spend millions to billions of years composing the chords we use. The loud events supernovae, kilonovae, are fast flourishes, but their debris takes its time, circling, collecting, trying again. Planets wait in disks that slowly learn how to build. Chemistry learns to fold and copy and signal. There's no hurry, and yet the results stack into forests, oceans, thought. The contrast throws our briefness into soft relief. We are quick by cosmic standards and, at the same time, the long game's local punctuation mark. Humility rides with that patience. The atoms we borrowed will continue their education elsewhere. The carbon you speak with tonight may someday rest in a limestone cliff or in a leaf on a planet you'll never see. The iron you carry may slip into soil. The hydrogen may rise as vapor and leave. We're not the end of the recipe. We are a course, served warm, quickly enjoyed, and then cleared to make room for what's next. This isn't loss, it's participation. Ancient stories intuited that the world's basics had personalities: fire's appetite, water's calm insistence, air's invisibility, earth's steadiness. Modern stories replace archetypes with measurements and models, and still end at the same door: belonging. The elements in us are not accidents. They are the natural outcomes of stars doing what gravity and time invite them to do. To look for meaning in the sky and hear the reply, "You are made of me," is both mythic and exact. The old thought experiment, imagine a universe without stars, makes our presence feel unlikely enough to be astonishing. If fusion never started, if hydrogen and helium never learned any new tricks, nothing like us would appear. The fact that gravity gathered, that the first faint cores lit, that explosions returned ingredients to the mix, that collisions minted rare metals. This stack of yeses is why water tastes clean, and apples are sweet, and a heartbeat can be heard through a stethoscope. We are the fortunate intersection of many processes that didn't have to meet but did. The ovens won't hum forever. Galaxies will dim. Kitchens will close. The table will hold what it holds, and no more. Life, if it persists, will cook with leftovers, reheating and reusing, making careful meals of what remains. Even then, matter will still tell its tales. Carbon will still be a spell cast in high heat. Oxygen will still be the sign of a helium age. Gold will still be a frozen shout from a rare collision. The handwriting of stars doesn't fade from atoms just because the authors have gone to sleep. That is far away. Tonight, the burners are still on. New worlds gather in rings of dust around young suns. Icy bodies write pale ellipses in the outskirts of systems. Clouds learn where to thicken. Somewhere, chemistry crosses a threshold and begins to copy itself. Somewhere else, it learns to sense light, then to move toward it, then to remember that motion. We live while the recipe is in motion. The kitchen is warm, the air smells faintly of ozone and rain, and we are lucky enough to taste. Take a breath and consider what you are holding. It's starlight, folded into water and muscle, fire cooled into bone and thought. It is a page of the universe's cookbook that happens to be open to you, knowing that the page will turn, and that pages turned are not pages lost. The narrative of the elements isn't just about nebulae and nova. It's about a glass raised to the lips, a hand on another hand, the long exhale at the end of a day. The atoms will keep their promises to the past and their appointments with the future. For a while, they keep you. The story of everything is a story of change that protects identity. From a bland beginning came a banquet. Stars were the patient chefs. They gathered simple ingredients, gave them time and heat, and taught them to be more than they were. They didn't hoard what they learned. They shared, sometimes gently, sometimes with fireworks, and the sharing made worlds. Those worlds got to try their own experiments, and one of them learned to listen in the dark and to name what it heard. Stand outside if you can, or stand at a window if you can't, and let your eyes adjust. The lights above are not just decorations, they are memories of work well done and work still in progress. You are looking at your own origins, shining from a respectful distance. The pulse you feel in your wrist is iron carrying oxygen, a rhythm kept by elements with long pedigrees. The ground underfoot is silica and aluminum and iron and calcium, all signed by stars. The water on your tongue is hydrogen from the beginning, clasping oxygen from a later chapter. The universe making a drink of its history. The night will end with morning, and the stars will fade in daylight, but their work will continue behind the blue. Galaxies don't wait for us, and they don't hurry because of us. They simply keep to their time, which is also ours, because we are made of them. The long fade, when it comes, will be gentle. It will be the quiet cooling of kitchens after a feast, the soft stacking of chairs, the lights dimmed room by room. Before that, there is still cooking to do and food to share.